Hi, I am Abhilash Pullanchiyodan, a Newton International Fellow from Bendable Electronics and Sensing Technology Group, University of Glasgow. Here I am going to present my work on metal-coated fabric-based supercapacitor. The content of today's presentation includes a brief introduction about wearable technology and energy storage, mainly focusing on textile-based energy storage technology, especially on metal-coated textiles and its biocompactability. Then we'll move on to today's work, that is metal coated fabric based supercapacitor. Here we are mainly discussing about device fabrication and structural analysis, followed by electrochemical characterization, then charging, discharging analysis, and finally conclusion. The wearable technology and energy storage. As the word indicates, the wearable technology is about wearing a technology. It can be anything from an electronic devices to a textile that is able to perform few tasks for the users. So what are the main characteristics for a wearable technology? First one is the wearability. The wearable technology is easily and safely can integrate with the skin of the user without causing any restrictions to the user normal activities. Then comes the functionality. The wearable technology is able to perform some tasks for the users. And then the durability, irrespective of the conditions and situations like mechanical deformation, the wearable technology is able to perform its functionality. Finally, the compactability. The compactability is the need of users, and that is mainly considered for the physical and aesthetic aspects. So the rapid enhancement happening in the electronic technology, different types of wearable devices are comes into picture like illuminated headwear, smart watches, fitness trackers, VR glasses, etc. So what the main requirement for this wearable electronics is the power management. So different types of power energy storage devices like supercapacitors and batteries are able to deliver this power requirement for this wearable electronics. Among these, the supercapacitor is supposed to be a suitable candidate for such application because of its high power density, easy to charge and discharge, and high cyclic stability. So based on the architecture consideration, we can mainly classify the wearable energy storage supercapacitors into three categories. First one is layered. Here the electrolyte is sandwiched in between the cathode and anode. Then comes the planar. Here both electrode like anode and cathode are in a single plane like an interdigitated structure. Then the electrolyte is placed on top of this one. Then finally comes the cable type architecture. Here both cathode and anode will be like a fiber electrode, and the electrolyte is covered on top of these two electrodes. So what are the main requirements for these wearable energy storage devices? Are mechanical stability, the washability, safety, it's a prime consideration. Then come comfort and breathability. So taking all these into account, the textile based energy storage device is supposed to be a suitable candidate for such application because the textiles are highly flexible and wearable. Its comfort, the high power structure of the textiles is able to enhance the capacitance. It's a low cost, it's scalable, the mass production is easily attainable in such cases, and it is easy to functionalize. The high aspect ratio of the textiles even help to enhance the capacitance. The good mechanical strength, especially in the wet condition, will be able to give more mechanical stability for the devices. The high absorption and desorption properties of the textiles eventually help to improve the energy density of the supercapacitor. Finally, it is easy to integrate. So some of the fabric-based or fiber-based supercapacitor that are reported in literature are shown here. In the first one, they use the carbon cloth as the substrate material, and the second and third one, they use the cotton as well as polyester fiber. Then they converted into a supercapacitive electrode by nickel coating as well as the reduced graphene oxide coating on the active electrode material. However, one of the main disadvantages of this supercapacitor based on the textile is the low conductivity of the textile. So in order to enhance the conductivity, researchers are trying to use metal coated textile for energy storage application. So the high conductivity of the metal will eventually enhance the conductivity of the supercapacitor as well as the capacitance of the devices. So these are some of the reported supercapacitors based on metal coated fabric. Here we can see different types of metal coated fabric. For example, in the first case, the nickel copper and nickel gold, and in the second case also the nickel copper nickel gold are used on the electrode as well as the current collecting material, whereas in the third and fourth case they use the copper as well as the nickel coated fabric for the supercapacitor application. As we discussed in the previous slide, one of the main aspects of the wearable supercapacitor is the safety, especially the biocompactability. So in the literature, if you can check, there is no experimental evidence which is showing the biocompactability, especially for the biocompactability of gel electrolytes are not available. So based on this aspect, we in our previous report, we have systematically investigated this biocompatibility aspect of a neutral gel electrolyte. So this is the overall picture of the reported work. Here we have fabricated a supercapacitor based on metal coated fabric of the electrode. Then we enhance the capacitor performance by including a graphite electrode in between on top of this metal coated fabric. Then finally we have investigated experimentally through the biocompactability of the formulated gel electrolyte through cytocompatibility test with the human dermal fibroblast cells. For that that studies, we have fabricated the devices. This is the device fabrication steps we have adopted. We have fabricated 3 devices, namely FSC1, FSC2 and FSC3. In FSC1 and FSC3 we use the metal coated fabric of the current collector, but in FSC3 apart from the metal coated fabric we use an additional layer of graphite for as an electrode to enhance the capacitance. But in the FSC2, in order to understand the role of metal coated fabric on the supercapacitor performance, we have used a non-metallized fabric, that is cellulose polyester as the substrate. Then we have made a device out of this fabric by using graphite coating. So the graphite coating will act as the electrode material as well as the current collecting applications. So some of the metal coated fabric used for the device fabrication are shown in the figure, and also the fabricated flexible supercapacitors given in the bottom figure. The structural and microstructural analysis as well as the electrochemical studies of this developed material were carried out. So from the structural and microstructural analysis, we come to know that the metal undergo electrochemical redox reaction during this electrochemical studies. So this redox reaction eventually forms the metal oxides that will help to enhance the capacitance through the Faraday capacitance formation. This is further evidence from the XRD analysis also. From the graphite coated electrode, we can clearly see the highly porous structure of the graphite electrode. This is responsible for high EDLC capacitance formation. The viscosity of the developed graphite ink as well as the XRD analysis of the graphite coated electrode also given the image. So the electrochemical studies of this metal coated fabric shows two fabric, namely Noradel and Armor FR, show the highest areal capacitance among all the 4 fabric under investigation. So we optimized or we finalize these 2 fabrics for further investigation. So we have fabricated the graphite coated electrode out of this Noradel and Armor FR and compared its performance with the cellulose polyester fabric coated with graphite electrode. So from the Nyquist plot, we can clearly see that the cellulose polyester fabric shows a high resistance of around 200 ohm compared with the metal coated fabric electrode, whereas the metal coated fabric electrode shows very low resistance of few ohms. So this low resistance of the metal coated fabric indicate the high performance of the supercapacitor or low ESR value. And from the board plot also we can see that the cellulose polyester with the graphite coating shows in EDLC formation the capacitance, whereas the metal coated fabric shows the EDLC as well as the Faraday capacitance. Then we have carried out the role of different electrolyte like neutral KCl, basic NaOH and acidic H3PO4 on the performance of this metal coated fabric, and the result are given in this figure. Then we have analyzed the biocompactability of the fabricated gel electrolyte with the HDFC cell. So the first row shows the cell growth of HDFC cell with the different days from day 1 to day 4. We can see that the cell growth is taking place in the medium. Then the same experiment we have carried out for the PVA-KCl medium also. In the PVA-KCl medium also we can see that with increasing the number of days, the HDFC cell, that is the human dermal fibroblast cell, shows a cell growth. So which conclude that the formulated PVA-KCl gel electrolyte is a biocompatible electrolyte. It doesn't show any cytotoxicity with the human dermal fibroblast cell, so it can be is safely used for wearable application. Then in order to show the practical utility of the fabricated devices, we have used to power the temperature sensor based on the devices as like a wristband, and we can see the result of the powering of the temperature sensor. The mechanical stability of the fabricated supercapacitor with the different bending radius also shows high capacitance retention in the mechanical deformation. This shows the lighting of an LED with the fabricated supercapacitor. Then come to the present work, that is metal coated fabric based supercapacitor. What we have done in here is that from the previous analysis we came to know that the maximum operational voltage we can achieve for this nickel and copper coated textile is around 0.5 volt because of the high redox reaction taking place on the nickel as well as copper. So in order to enhance the operational voltage, here we have selected silver coated textile, that is Berlin. Then we have fabricated a wearable supercapacitor in the same approach we have discussed previously. From the structural studies, we can conclude the silver as well as the carbon or graphite phase in the fabricated electrode. The microstructure also shows the high porous structure, which is eventually help to enhance the capacity. The electrochemical studies shows that the graphite coating slightly increases the resistance, but still it's in a very low value of around few ohms. The capacitance value shows a double and time enhancement in the capacitance after graphite coating. This is even visible from the CV as well as GCD analysis. The variation of the CV curve with different scanning rate also shows a more of EDLC type double layer formation with a small redox peak around 0.1 volt, which arises from the redox reaction taking place in the silver metal. And the variation of the supercapacitance, areal capacitance with the scan rate also shows the graphite coated devices shows a almost double time capacitance when compared with non-graphite coated fabric. The charging discharging analysis of the fabricated devices in different applied current as well as the different potential windows given here, and the corresponding Ragan plot also shown in the picture. So the table shows the variation of the areal capacitance, energy density as well as IR drop of the fabricated BGr-FSC with a different voltage window from 0.5 to 1.2 volt. As we can see, with increasing the voltage window, the areal capacitance as well as the energy density shows a linear increase. The IR drops also slightly increases with this increasing voltage window. A conclusion, we have fabricated a fabric-based supercapacitor using silver-coated textile as the substrate as well as the current collector. The supercapacitor performance of the device is improved with a uniform layer graphite paste printed on the fabric. The structural and microstructural analysis of the fabric without and with the graphite coating was carried out. The electrochemical and GCD analysis were carried out. PVA gel was used as electrolyte for supercapacitor fabrication to meet the user safety for wearable application. And going forward, it will be worth explain the fabric supercapacitor for safer bioelectrolyte like body fluids such as sweat, etc. Finally, I would like to acknowledge the best group for support for carrying out this research, and I would like to acknowledge our research funders. And finally, for IEEE Plus for giving an opportunity to present my work in this conference. Thank you for your attention.